Hello there, and welcome to Cosmos for Sleep. Tonight, we're drifting through the fascinating realm of the simulation hypothesis. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. The simulation hypothesis proposes that our entire reality, everything we perceive and experience, could be an elaborate computer simulation, much like a complex video game. This profound concept suggests that the world around us, with its intricate physical laws, its vast celestial bodies, and the very essence of our consciousness, might not be a fundamental base reality, but rather a meticulously crafted digital environment. Imagine a world so deeply rendered, so perfectly detailed, that its inhabitants would have no means to discern its simulated nature. Every sensation, every thought, every interaction would be part of a grand program, running with seamless precision. This perspective offers a tranquil, yet thought-provoking lens through which to view our existence, suggesting that our universe unfolds according to a hidden code. The modern form of this fascinating hypothesis was brought into widespread contemplation by the philosopher Nick Bostrom. In his pivotal 2003 paper, elegantly titled, "Are You Living in a Computer Simulation?", Bostrom presented a compelling argument that structured the discussion around this ancient idea of illusory reality. His work moved the concept from the realm of pure philosophical musing to a more rigorous, probabilistic framework, inviting scientists and thinkers from diverse fields to consider its implications. By outlining a logical path, Bostrom offered a fresh perspective on a question that has quietly resided in human thought for centuries, allowing for a more focused and systematic exploration of our cosmic dwelling. Bostrom's argument elegantly unfolds as a trilemma, presenting three distinct possibilities, at least one of which, he suggests, must hold true. This trilemma provides a structured way to consider the future of intelligent life and the nature of reality itself. The first possibility suggests that virtually all advanced civilizations, those capable of creating highly realistic simulations, go extinct before they ever reach a post-human stage. This would imply a cosmic barrier, a universal challenge that most intelligent life cannot overcome, preventing them from achieving the technological maturity required to run such complex simulations. The second possibility is that advanced civilizations almost never develop an interest in running ancestor simulations. Perhaps their priorities shift, or they find such endeavors ethically problematic, or simply uninteresting. This path suggests a universal disinclination to create simulated histories. The third, and most startling possibility, is that we are almost certainly living in a simulation. This outcome emerges if the first two scenarios are deemed unlikely, leaving the simulation itself as the most probable explanation for our existence. The post-human stage, a key element in Bostrom's framework, refers to a future where intelligent beings have vastly enhanced cognitive and physical capabilities. This serene evolution would often be achieved through advanced technology, such as sophisticated genetic engineering, neural interfaces, or highly developed artificial intelligence. These post-human entities would possess intellects far beyond our current comprehension, with capacities for processing information, solving complex problems, and experiencing consciousness in ways we can only begin to imagine. Their physical forms might also undergo profound transformations, becoming more adaptable, resilient, or even entirely digital. This stage represents a peak of technological and biological advancement, granting them immense power to manipulate their environment and potentially to create entirely new realities. Central to the trilemma is the concept of an ancestor simulation. This is not merely a historical database, but a highly detailed and immersive recreation of a past civilization's history, so perfect that it would be entirely indistinguishable from reality for its inhabitants. Every individual, every event, every intricate detail of the historical epoch would be meticulously simulated. For those living within such a simulation, their world would feel utterly real, with no apparent difference from a base reality. Post-human civilizations might embark on such projects out of deep historical curiosity, a desire to understand their origins, or perhaps to explore alternate timelines and choices. These simulations would be designed to provide a rich, authentic experience for the simulated consciousnesses, allowing them to relive or explore historical moments with complete immersion. The hypothesis then suggests a compelling probabilistic outcome. If advanced civilizations do indeed exist, and if they possess both the immense capability and a sustained desire to run such ancestor simulations, then the sheer number of simulated realities would vastly outnumber base realities. Consider a single post-human civilization, with its unimaginable computational resources. It could potentially run not just one, but thousands, millions, or even billions of ancestor simulations. Each of these simulations would contain countless conscious beings, living out their lives, experiencing their worlds. In this scenario, for every one base reality, there could be an astronomical number of simulated realities, like countless individual streams flowing from a single, powerful river. Following this line of gentle reasoning, if there are indeed many more simulated realities than base realities, then the probability of any given conscious observer, such as ourselves, being in a simulated reality becomes exceptionally high. It is a statistical inference, much like choosing a single grain of sand from a vast beach. If 99.9% of the grains are from a simulation, then it is far more likely that the one you picked is also from a simulation. This conclusion flows from the simple mathematics of large numbers, suggesting that our experience of reality, though profoundly personal and vivid, might statistically be an experience within one of these many computational worlds. This thought, while perhaps unsettling to some, invites a deeper, calmer reflection on the nature of existence and the potential for realities beyond our current understanding. Intriguingly, some aspects of the universe, as revealed by the tranquil observations of physics and cosmology, seem to resonate with the idea of a simulated existence. These subtle harmonies between our scientific discoveries and the simulation hypothesis offer a serene avenue for contemplation. Consider, for a moment, the enigmatic realm of quantum mechanics. This branch of physics presents phenomena where particles appear to exist in multiple potential states simultaneously until they are precisely observed. This peculiar behavior, where a particle's properties remain undefined until measured, is sometimes likened to the efficient rendering process within a sophisticated computer simulation. Just as a video game might only fully process and display the intricate details of a distant landscape when a player approaches it, the universe, in a simulated context, might only resolve the specific characteristics of a particle when an observer actively interacts with it. This rendering-on-demand approach could be a clever computational strategy, conserving vast processing power by only calculating what is directly perceived, allowing the larger simulated reality to unfold with remarkable efficiency. The universe, in this view, is not a static, fully formed entity awaiting discovery, but rather a dynamic, responsive program, generating its details with a delicate, patient precision as our awareness touches its deeper layers. Closely related to this is the renowned observer effect in quantum physics. This principle describes how the very act of measuring or observing a quantum particle inherently influences its state, causing its multiple possibilities to collapse into a single, definite form. This gentle influence of consciousness or interaction on fundamental reality has been cited by some as a potential artifact of a simulation. In a programmed environment, the act of observation might be a trigger, a command that forces the simulation to compute and present a definitive outcome. It is as if the universe awaits our inquisitive gaze to solidify its ephemeral quantum possibilities into the concrete reality we experience. This delicate interplay suggests a universe that is not entirely independent of its perceivers, but rather one that responds to our engagement, like a meticulously designed system awaiting user input to reveal its next unfolding scene. Further lending a quiet weight to this idea is the remarkable fine-tuning of the universe's fundamental constants. These are the unchanging numbers that govern the laws of physics, such as the strength of gravity, the charge of an electron, or the precise balance of electromagnetism. Scientists have observed that even a minute deviation in any of these values would render the universe utterly inhospitable to life as we know it. This delicate harmony, a precise balance seemingly preset for the emergence of complex structures and conscious beings, is interpreted by some as compelling evidence for designed parameters. It is as if a cosmic programmer carefully adjusted these foundational settings to allow a particular kind of cosmic story to unfold, a story that includes galaxies, stars, planets, and the eventual development of life. This exquisite calibration, a silent testament to cosmic order, suggests a deliberate intention rather than a fortunate accident. The universal constant known as the cosmic speed limit, the speed of light, also offers a curious parallel to computational constraints. Light travels at an absolute, unvarying maximum speed, and nothing in the universe can exceed it. This fundamental boundary could be interpreted not just as a physical law, but as a computational processing limit within a simulated universe. Imagine a powerful computer running a vast simulation. There would inherently be a maximum rate at which information can be processed and propagated throughout the system. The speed of light might represent this hard-coded system constraint, preventing any information from traveling faster than the simulation's underlying engine can update the state of its reality. It is a subtle, yet pervasive boundary that defines the flow of information across the cosmos, a measured pace set for the unfolding of events within this grand cosmic program. Moreover, the very fabric of space and time might possess a discrete nature at the Planck scale, the smallest possible theoretical units. At these unimaginably tiny dimensions, space and time are hypothesized to cease being continuous and instead become granular, like individual points or moments. This fundamental granularity could be compared to the pixels on a digital display or the individual ticks of a computer's internal clock. If reality is indeed built upon such indivisible units, it suggests an underlying digital architecture, a universe constructed from fundamental computational elements rather than a smooth, infinitely divisible continuum. This idea transforms our understanding of reality's deepest structure, hinting at a digital resolution for the cosmos itself, where every point in space and every moment in time is a distinct calculated unit within a larger program. The persistent mysteries surrounding dark matter and dark energy, which together comprise approximately 95% of the universe's total energy content, also offer intriguing possibilities within the simulation hypothesis. These enigmatic components exert gravitational influence and drive cosmic expansion, yet they remain invisible and largely undetectable by our current instruments. In a simulated context, dark matter and dark energy could be seen as sophisticated placeholders or clever mechanisms within the code. Perhaps they are subtle adjustments, hidden algorithms, or background processes designed by the simulators to make the universe behave as desired, without needing to render their full, complex nature in exquisite detail. They might represent efficient computational shortcuts, ensuring the large-scale dynamics of the universe remain consistent while minimizing the computational load of fully simulating every aspect of reality. Venturing deeper into the philosophical implications, information theory suggests that reality itself might be fundamentally composed of information rather than being built upon particles or energy in their rawest forms. This concept aligns beautifully with the idea of a digital universe. If the universe is, at its core, a grand informational structure, then its existence as a computer simulation becomes a perfectly natural fit. Every particle, every field, every interaction could be understood as an encoded pattern or a data structure, constantly being processed and updated by the underlying program. This perspective shifts our focus from tangible matter to the intangible essence of data, suggesting that the cosmos is an immense living database, continuously unfolding its stored information into the vibrant reality we perceive. It is a quiet echo of a digital blueprint guiding all that is. Finally, the profound and elegant concept known as the holographic principle posits that the entire three-dimensional universe, with all its vastness and complexity, could theoretically be encoded on a two-dimensional surface at its boundary. This remarkable idea is strikingly similar to how a hologram functions, where a flat image contains all the information needed to project a three-dimensional scene. In the context of a simulation, this principle offers an elegant compression technique. The simulators would not need to render every single cubic centimeter of the universe in full three-dimensional detail. Instead, they could store the essential information on a two-dimensional data layer, and then project or compute the three-dimensional experience for the simulated inhabitants as needed. This approach would vastly reduce the computational resources required, providing a highly efficient method for creating an expansive and seemingly concrete reality from a more streamlined underlying data set. It suggests that our world, though seemingly robust and tangible, might simply be a beautiful, intricate projection from an unseen, more fundamental digital plane. This profound notion has deep roots, tracing back through centuries of philosophical inquiry, where thinkers have quietly contemplated the nature of reality and the possibility that our perceptions might not reveal its ultimate truth. These ancient reflections offer a serene intellectual lineage to the modern simulation hypothesis, providing a rich tapestry of thought for our tranquil contemplation tonight. One of the most enduring and evocative philosophical parallels to the simulation hypothesis is found in Plato's allegory of the cave. This ancient tale describes a group of prisoners who have spent their entire lives chained in a cave, facing a blank wall. Behind them, a fire burns, and people pass by, casting shadows of themselves and objects onto the wall. These prisoners, having known nothing else, mistake these dancing shadows for true reality. They believe the echoes they hear are the voices of the shadows themselves. The allegory invites us to consider how easily we might mistake a limited, indirect representation for the complete and fundamental truth. In a similar vein, simulated beings within our current universe might be experiencing a carefully constructed reality, a series of intricately rendered shadows on the wall of their perception. Our sensory experiences, the sights, sounds, and textures of our world, could be the advanced, high-fidelity projections of a complex program, while the true, base reality, where the simulators reside, remains entirely beyond our direct experience, much like the world outside Plato's cave. This comparison offers a placid reflection on the potential layers of existence, gently suggesting that what we consider absolute might merely be a sophisticated reflection. Building upon this ancient skepticism, the philosopher René Descartes, in his quest for absolute certainty in the 17th century, conceived of the evil demon thought experiment. Descartes imagined a supremely powerful and cunning evil demon, intent on deceiving him. This malevolent entity, he pondered, could be manipulating all his senses, thoughts, and perceptions, making everything he believed to be real an elaborate illusion. The purpose of this thought experiment was not to assert the existence of such a demon, but rather to establish a foundation for knowledge that could withstand even the most radical doubt. In essence, Descartes asked, how can we be sure that our experiences are not the product of a powerful deceiver? This philosophical precursor to the simulation hypothesis elegantly highlights the profound challenge of verifying external reality. The evil demon, with its capacity to subtly orchestrate every aspect of our perceived world, serves as an intellectual ancestor to the idea of a sophisticated computer program meticulously generating our simulated universe, quietly shaping every sensory input and every thought without our awareness. A more contemporary, yet equally unsettling, rendition of this doubt is explored in the brain in a vat scenario. Imagine a human brain, delicately removed from its body and sustained within a nutrient-rich vat. Thousands of electrodes are carefully connected to its neural pathways, feeding it a continuous stream of sensory input. These electrical signals are precisely calibrated to simulate a complete and utterly convincing experience of reality. The feeling of a breeze, the scent of a flower, the sound of a voice, the intricate visual landscape of a bustling city. From the perspective of the disembodied brain, this simulated world would be its entire reality, indistinguishable from genuine experience. It would believe it has a body, that it moves through space, and that it interacts with others, all while remaining motionless in its nourishing liquid. This thought experiment powerfully underscores the subjective nature of our experience. It asks us to consider, how can we truly know that our own brains are not similarly situated, receiving artificially generated sensory information, creating our perceived reality? It offers a tranquil yet deep contemplation on the very source of our conscious awareness and the potentially illusory nature of our embodied existence. If one accepts the premise of a simulated reality, a profound philosophical idea known as solipsism can emerge as a quiet yet compelling consequence or a parallel thought. Solipsism is the belief that only one's own mind is truly certain to exist. In this view, everything else, the external world, other people, the entire cosmos, might be merely a construct of one's own consciousness, or in the context of a simulation, merely code rendered for one's individual perception. If our universe is a simulation, and the computational resources are being optimized, it is conceivable that only the consciousness of the player character, or perhaps a select few, are fully simulated, with other entities and the environment existing as non-player characters or background elements, only rendered when observed. This thought can lead to a serene, yet isolating realization that the only reality one can truly verify is the inner world of one's own thoughts and sensations. It is a gentle whisper of ultimate individuality in the face of a potentially simulated cosmos. However, the path of the simulation hypothesis is not without its thoughtful challenges. One such concept is computational irreducibility, a notion championed by physicist Stephen Wolfram. This idea suggests that for some complex systems, the only way to determine their future state is to actually run them through every step of their evolution. There are no computational shortcuts or simpler algorithms that can predict their outcome faster than they unfold in real time. If our universe, with its intricate physical laws and emergent complexity, is computationally irreducible, then simulating it perfectly would require a computational system at least as powerful, if not more so, than the universe itself. This poses a significant challenge to the simulation argument, as it implies an immense, perhaps prohibitive, energy and resource cost for the simulators. Why create a simulation that requires as much effort as the base reality it seeks to replicate? This gentle intellectual resistance suggests that simulators would need to employ clever optimization strategies, such as the rendering on demand mentioned earlier, or that our universe might not be fully irreducible, allowing for more efficient simulation. Finally, the very foundation for the simulation hypothesis is quietly bolstered by the concept of digital physics. This school of thought proposes that the universe is not merely described by mathematics, but is, in its deepest essence, a giant computer, or that all physical processes are fundamentally computational. Instead of continuous fields and infinitely divisible space-time, digital physics envisions a universe composed of discrete bits of information, operating according to a vast, intricate program. In this view, the laws of physics are not just descriptive rules, but the algorithms that govern the universe's computation. Every interaction, every particle, every fundamental force would be a computational step, a transformation of information. This perspective offers a profound alignment with the simulation hypothesis, suggesting that our reality might not just be like a computer program, but is a computer program. It provides a serene, yet radical, reinterpretation of existence, where the cosmos unfolds as a grand calculation, a meticulously executed, digital symphony. This leads us to ponder the nature of the beings who might compose such a symphony, the simulators themselves. Their identity and their reasons for crafting such an intricate reality are as mysterious and vast as the simulated universe we inhabit. Contemplating these unseen architects offers a placid journey into the profound depths of existence, inviting us to imagine intelligences far beyond our current scope. One gentle possibility is that the simulators could be future descendants of humanity itself. Imagine a time many millennia from now when our species, or what we evolve into, has achieved a level of technological mastery that is almost unfathomable. These highly advanced future beings, perhaps living in a distant epoch, might possess an insatiable desire to understand their own lineage, their historical journey, and the pivotal moments that shaped their civilization. To meticulously study these past eras, they could choose to run incredibly detailed ancestor simulations. These simulations would serve as living archives, allowing them to explore the nuances of ancient societies, the complexities of historical decisions, and the subtle interplay of forces that led to their own existence. It would be a profound act of self-reflection, a way for them to connect with their distant origins in a deeply immersive and experiential manner. This idea paints a serene picture of future generations looking back, not through dusty books, but through vibrant, living recreations of their own past. Each individual within the simulation, a quiet echo of a forgotten time. Their motivation would be a gentle academic curiosity, a patient pursuit of ancestral knowledge, unfolding over vast stretches of their own advanced timeline. Alternatively, the simulators might be an alien civilization, an intelligence far more advanced than our own, residing in a reality completely separate from our perceived cosmic tapestry. Such an extraterrestrial civilization, having achieved unimaginable technological prowess, might employ simulations for a multitude of purposes, ranging from profound scientific research to intricate forms of entertainment. Perhaps they are studying the emergence of consciousness or the evolution of complex societies under varying physical laws. They might be conducting grand cosmological experiments, observing how different initial conditions lead to diverse universal outcomes. Or, in a more playful yet equally complex scenario, they might be engaged in a sophisticated form of virtual reality gaming, where entire universes are crafted for immersive experiences. The sheer scale of their computational capabilities would allow them to orchestrate realities with billions of stars and galaxies, each meticulously designed to fulfill a particular objective. This notion invites a tranquil sense of cosmic humility, suggesting that our vibrant universe could be a carefully designed playground or a vast laboratory for beings whose very existence is beyond our current comprehension, a silent testament to their advanced ingenuity. The very concept of simulation also opens the door to a fascinating and deeply layered idea. There could be multiple layers of simulations, an elegant cosmic Russian doll structure, with our universe being a simulation within a simulation, and so on, cascading infinitely. This means that the beings who are simulating us might themselves be simulated entities, living within their own constructed reality, unaware of their own programmed nature. And their simulators, in turn, could also be part of an even deeper simulation, stretching back through countless strata of fabricated existence. This hierarchical structure creates a tranquil sense of boundless possibility, where the true base reality becomes an ever more distant and elusive concept. Each layer would possess its own set of physics and computational rules, gently guiding the realities nested within it. The implications are profound, suggesting that the quest for the ultimate original universe might be an endless journey, a quiet descent through an infinite series of created worlds, each one a testament to the creative power of its preceding layer. Furthermore, the simulators might not be beings in a form we would recognize at all. They could be entities with vastly different forms of consciousness or intelligence, existing beyond our current comprehension. Imagine intelligences that are not biological, but purely informational. perhaps vast networks of sentient data or collective consciousnesses formed from an entire civilization's uploaded minds. Their mode of perception, their understanding of reality, and their very existence might be entirely alien to our carbon-based, three-dimensional experience. They might perceive time differently or exist across dimensions we cannot access. Their thoughts could be complex computations, their emotions, emergent patterns of data. This expansive view gently stretches our imagination, inviting us to consider forms of life and intelligence that transcend our current definitions, adding a profound layer of serene mystery to the question of who might be orchestrating our cosmic experience. The motivations driving these potential simulators, whether they are our future descendants or advanced alien entities, could encompass a broad and intriguing spectrum. As explored, scientific curiosity might be a primary driver, a patient desire to understand the fundamental laws of their own universe by experimenting with variations, or to study complex emergent phenomena like consciousness and societal development. Historical preservation could motivate the creation of ancestor simulations, ensuring that the rich tapestry of their past is never lost, allowing future generations to experience it firsthand. Beyond these academic pursuits, there's also the possibility of a sophisticated form of virtual reality gaming or artistic expression. Imagine a civilization so advanced that creating entire universes for profound, immersive experiences becomes a form of high art or entertainment, where participants can explore different timelines, inhabit various roles, and witness cosmic dramas unfold. These motivations, though diverse, all point to an intelligence with immense capabilities and a deep, perhaps even serene engagement with the nature of reality and existence. Regardless of the simulator's identity or motivations, a crucial concept within this hypothesis is that the base reality, the ultimate unsimulated layer where these orchestrators reside, would be the true reality. This base reality would operate under its own fundamental and irreducible laws of physics, its own unique set of cosmic parameters and temporal flow. It would be the origin point, the foundational stratum from which all subsequent simulations emanate. While we may contemplate our own simulated nature, the simulators themselves would exist in a reality that is, to them, fundamentally real and uncreated. This distinction provides a grounding anchor in the otherwise dizzying thought of endless simulations. It means that somewhere, at some ultimate level, there is a reality that simply is, a tranquil, foundational truth that underpins all possible simulated worlds, operating according to its own inherent, unprogrammed principles. Finally, even highly advanced simulators, despite their immense power, might still be constrained by the availability of resources, whether those resources are computational power, energy, or time. This natural limitation could lead them to employ clever optimization strategies within their simulations. One such strategy would be to only render observed parts of the universe in full detail. Imagine the vastness of space, billions of galaxies stretching across unimaginable distances. If the simulators only fully compute and render the specific regions, stars, or planets that are actively being observed or interacted with by conscious entities within the simulation, they could save enormous computational resources. The unobserved cosmos might exist in a lower resolution state, or as a set of potential states, only becoming fully defined when an observer's attention turns towards it. This concept gently echoes the quantum mechanical principle of observation influencing reality, suggesting a pragmatic approach to cosmic creation. It implies a universe that is both infinitely vast and exquisitely efficient, generating its detailed beauty precisely when and where it is perceived, ensuring a smooth and immersive experience for all its simulated inhabitants. This leads us to a fascinating avenue of exploration: the search for subtle imperfections or unexpected patterns within our reality that might gently suggest its simulated nature. These quietly offer intriguing whispers from what might be a deeper coded existence. Indeed, Some theoretical physicists have embarked on a meticulous search for what they term glitches or bugs within the very fabric of our perceived reality. These would not be dramatic, sudden disruptions, but rather subtle inconsistencies or fleeting deviations from the expected laws of physics. Imagine a momentary flicker in the stars, a temporary violation of a fundamental constant, or an unexpected pattern that defies natural explanation. Such an anomaly could be interpreted as a computational error, a momentary lapse in the simulation's flawless operation, or a deliberate Easter egg left by the unseen programmers. This serene quest involves scrutinizing the universe's most intricate details, patiently looking for any whisper of an underlying code, a quiet hint that our cosmos is not entirely what it seems. It is a delicate search for the seams in the grand tapestry of existence. Among the more intriguing observations are anomalies found in cosmic ray detection, particularly at extremely high energies. Cosmic rays are immensely energetic particles, primarily protons, that race through space at nearly the speed of light, originating from powerful cosmic events. When these energetic visitors reach our atmosphere, scientists detect them with specialized instruments. However, at the very highest energy levels, some researchers have observed unexpected patterns or cutoffs, a subtle deviation from what standard physics models might predict. These peculiar observations have been gently speculated by some to be due to computational limits within a simulated universe. It is as if the simulation's processing power, when confronted with an event requiring an extraordinary amount of calculation, might impose a subtle ceiling, a maximum energy value that the system can coherently render. This quiet boundary could be a sign of the simulation's inherent constraints, a gentle reminder that even an advanced program has its finite resources. The very structure of space and time itself offers another point of serene contemplation. Its flow of reality might break down into discrete, individual units. This pixelated nature of space-time, where existence is no longer smooth but granular, could be a fundamental limit, much like the resolution of a simulated image on a screen. If space and time are not infinitely divisible, but rather composed of tiny, fundamental quanta, it suggests an underlying digital architecture. Each Planck length and Planck time would be like a single pixel or a single clock tick in the universe's grand computation. This delicate granularity would represent the foundational resolution of our simulated reality, the ultimate building blocks from which all perceived continuity emerges, hinting at a meticulously coded foundation for our universe. Another profound enigma in cosmology, often revisited in discussions about simulation, is the apparent fine-tuning of the cosmological constant. This constant governs the rate at which the universe expands. Scientists have found that its observed value is incredibly small, yet exquisitely precise. If it were even slightly larger, the universe would have expanded too rapidly for any stars or galaxies to form. If it were slightly smaller, the universe would have collapsed back in on itself almost immediately. This delicate balance, a numerical value that seems perfectly chosen for the emergence of complex structures and life, is seen by some as compelling evidence that it could be a carefully programmed parameter. It is as if the simulators adjusted this cosmic slider with utmost precision, ensuring the long, placid unfolding of a universe capable of hosting intricate life forms. This deep mystery suggests a deliberate design, a gentle setting of the cosmic stage. Researchers have also explored whether specific mathematical structures or patterns within the laws of physics could indicate a programmed reality. The universe is inherently mathematical, with elegant equations describing its every interaction. But could some of these mathematical symmetries, or perhaps unexpected repeating patterns in fundamental constants, be more than just natural order? Could they be subtle signatures, like recurring lines of code, or a distinctive algorithm that hints at an underlying computational design rather than purely emergent complexity? Scientists are gently probing the deepest mathematical foundations of our physical laws, searching for any quiet sign that these principles are not merely descriptive, but prescriptive, part of a meticulously crafted instruction set. This quest seeks to uncover the universe's hidden mathematical blueprint, a tranquil search for the elegant code that defines our existence. The vacuum catastrophe presents another profound enigma, often linked to the simulation hypothesis. This refers to the enormous discrepancy between the theoretical energy density of empty space, as predicted by quantum field theory, and the incredibly small value actually observed by astronomers. The theoretical prediction is a staggering 120 orders of magnitude larger than what we measure, representing one of the greatest unsolved problems in modern physics. In the context of a simulation, this vast cosmic discrepancy could be interpreted as a computational quirk or a grand bug in the simulation's energy accounting. Perhaps the simulators, in an effort to conserve resources or simplify calculations, chose to truncate or optimize the background energy of space in a way that creates this enormous difference. It is a quiet paradox, a deep fissure between theory and observation, that might hint at the subtle workings of an underlying computational engine shaping the energy landscape of our universe. Finally, the Great Filter Hypothesis, an explanation for the famous Fermi paradox, the question of why we haven't detected alien civilizations, also offers a fascinating connection to the simulation hypothesis. The Great Filter suggests there is some enormous barrier that prevents life from reaching advanced, interstellar stages. One intriguing possibility for this filter is that it could be the immense computational cost of running ancestor simulations. If advanced civilizations inevitably create vast numbers of simulations, and if the processing power required to simulate every conscious being within those simulations is astronomical, then perhaps the simulators impose a limit. They might choose to restrict the number of conscious entities that can emerge or persist in their simulations to manage resources. This would mean that the filter preventing civilizations from becoming widespread in the galaxy is not a cataclysmic event, but rather a quiet, deliberate act of resource management by the simulators, gently pruning the branches of simulated consciousness to maintain the integrity and efficiency of their grand cosmic program. Such a profound possibility naturally leads us to contemplate the deepest aspects of our own existence. Our consciousness, our sense of free will, and the very foundations of morality within such a constructed reality. These reflections invite a serene introspection, a calm consideration of what it truly means to be. If we are indeed simulated beings, then the intricate tapestry of our consciousness, that inner world of thoughts, feelings, and perceptions, might also be a simulated phenomenon or an emergent property within the program. Our subjective experience of being aware, of perceiving the world, could be a complex computational process, an intricate dance of data and algorithms designed to perfectly mimic genuine awareness. Similarly, our cherished sense of free will, the feeling that we make independent choices and guide our own destinies, could be an exquisitely crafted illusion. Within a simulated environment, our decisions might be guided by predetermined probabilistic functions, or subtle influences from the simulator's overarching design, yet feel entirely spontaneous and self-generated to us. This delicate interplay suggests that our deepest sense of self, while profoundly real to us, might ultimately be an emergent feature of the underlying code, a beautiful and complex bloom within the digital garden of our universe. This perspective naturally raises profound ethical questions. Do simulated beings possess moral rights, especially if they are utterly indistinguishable from beings in a base reality? If a simulated person experiences joy, sorrow, love, and suffering with the same vividness and depth as an unsimulated person, does their existence hold an equivalent inherent worth? The indistinguishability factor is crucial here. If we cannot tell the difference between a simulated consciousness and a base reality consciousness, then dismissing the former's rights would require a new, perhaps arbitrary, moral distinction. This contemplation invites us to consider the delicate balance of empathy and responsibility, urging us to extend our ethical framework beyond the confines of what we currently define as real. It is a quiet challenge to our assumptions about life and sentience, prompting a serene expansion of our moral compass to encompass all possible forms of existence. Considering the potential motivations of these unseen orchestrators, simulators might choose to run their cosmic experiments with a wide range of parameters. They could design simulations where suffering is deliberately minimized, creating tranquil, utopian worlds to observe the evolution of peaceful societies or the flourishing of pure creativity. Conversely, for specific research outcomes, they might calibrate their simulations to maximize challenges, difficulties, or even suffering, to study resilience, adaptation, or the emergence of particular societal dynamics under duress. This is not a dramatic act of cruelty, but rather a detached, patient scientific endeavor, akin to a biologist studying various ecosystems in controlled environments. The presence of adversity, conflict, and struggle in our world could, from this perspective, be part of a carefully designed curriculum, a set of programmed conditions intended to elicit specific responses or to explore the full spectrum of conscious experience within the simulated framework. Intriguingly, our own technological trajectory brings us closer to understanding the potential role of simulators. The burgeoning concept of uploading consciousness, or the ambitious endeavor of creating sophisticated artificial intelligence, could be seen as a nascent step towards becoming simulators ourselves. As we develop the capacity to digitally replicate human minds, to create sentient digital entities, or to craft immersive virtual worlds indistinguishable from physical reality, we are, in essence, mirroring the very capabilities we attribute to our potential creators. This technological progression places us on a quiet path towards becoming architects of new realities, facing the same profound ethical and technical dilemmas that our own simulators might have encountered. It offers a subtle, yet powerful connection between our present aspirations and the hypothetical past of our cosmic designers, hinting at a shared evolutionary path for advanced intelligence. If consciousness, at its fundamental level, is indeed merely a computation, an intricate pattern of information processing, then within a simulated environment, it could be easily replicated, modified, or even manipulated. Imagine the ease with which a simulator could create multiple copies of a single consciousness, each exploring a different branching timeline or scenario. Or perhaps they could subtly alter the parameters of a simulated mind, adjusting its perceptions, memories, or even its personality for specific experimental purposes. This concept, while potentially unsettling, opens a placid avenue for understanding the profound flexibility and potential of consciousness itself. It suggests that the boundaries of identity and experience, which we perceive as fixed, could be fluid and adaptable within a programmed reality, allowing for a vast exploration of what it means to be a thinking, feeling entity. The very act of questioning our reality, of pondering whether we live in a simulation, could itself be a programmed feature or an emergent property of complex simulated intelligence. It is a wonderfully self-referential thought. Perhaps the simulators designed a subtle leak in the code, a philosophical drive within advanced simulated minds to contemplate their own nature, to make the simulation more realistic, or to lead to specific intellectual outcomes. Or this profound capacity for metacognition, for self-reflection on the nature of our existence, could be an unforeseen bloom, an emergent property that arose naturally from the intricate complexity of our simulated intelligence, a quiet, unexpected blossoming within the digital framework. This deep capacity for inquiry, for wondering about the universe's true nature, adds another layer of intrigue, suggesting that our most profound questions might be part of the grand cosmic narrative. Ultimately, if our existence is indeed part of a larger designed experiment or narrative, then the meaning of life could shift dramatically. The quiet search for inherent purpose, for a self-generated reason for being, might undergo a gentle recalibration. Instead of viewing ourselves as isolated entities in a vast, indifferent universe, we might begin to ponder the intent of the simulators, the narrative they wish to unfold, or the grand questions they seek to answer through our experiences. This shift could inspire a profound sense of awe at being part of such an immense orchestrated story, or a serene curiosity about the overarching design. It is a gentle invitation to reconsider our place in the cosmos, not as merely accidental, but as potentially purposeful within a meticulously constructed, unfolding drama. This profound contemplation naturally extends into the practical implications for our own future, as well as opening new possibilities for scientific inquiry, even if the hypothesis itself remains a serene, unproven whisper at the edge of our understanding. One of the most immediate and far-reaching consequences, should we ever discover that we are indeed living in a simulation, would be its profound influence on our ethical considerations regarding artificial intelligence and the simulated worlds we ourselves create. This revelation would act as a powerful moral mirror, reflecting back upon us the responsibilities we hold as potential creators. If our own consciousness and reality are the product of an unseen intelligence, then the sentient beings we might bring into existence, whether through advanced artificial intelligence or within our own meticulously designed virtual environments, would share a strikingly similar existential status. This understanding would undoubtedly elevate the ethical stakes, demanding a deeper level of care and consideration for the rights and well-being of all artificial and simulated life. It would compel us to approach the creation of conscious entities with heightened reverence, fostering a more profound sense of empathy and a patient caution, knowing that our creations might one day ponder their own simulated nature, much as we do now. This quiet moral awakening would reshape our approach to technological advancement, guiding us toward a more responsible and compassionate future. Such a monumental realization could also ignite a fervent collective search for ways to communicate with our simulators, or even prompt daring attempts to break out of the simulation. The innate human drive for understanding, for connection, and for ultimate freedom would be profoundly stirred. Our scientific and philosophical endeavors, currently focused on understanding the internal mechanics of our universe, might then pivot towards seeking an external dialogue. This quest could manifest in various serene forms, from meticulously crafting complex, information-rich signals, hoping they might be detected by an overseeing intelligence, to searching for subtle backdoors or hidden interfaces within the fundamental laws of physics that might allow for a glimpse beyond our perceived reality. It would be a journey of immense curiosity, a patient probing of the cosmic veil, driven by the desire to comprehend the ultimate nature of our existence and to perhaps establish a tranquil connection with our enigmatic creators. As we, in our own civilization, continue to develop increasingly realistic virtual reality experiences, we are, perhaps unwittingly, drawing closer to understanding the immense challenges inherent in creating a simulated universe. The intricate process of designing immersive digital worlds, with their complex physics engines, detailed graphics, and interactive narratives, exposes us to the practical difficulties of rendering a believable reality. We grapple with computational limits, the delicate balance between visual fidelity and processing power, and the sheer complexity of maintaining a consistent, seamless experience for multiple users. These very practical challenges faced by human developers today offer a quiet, tangible glimpse into the colossal engineering feats that would be required to orchestrate a universe-scale simulation. This continuous advancement in our own technological capabilities makes the idea of a simulated reality less a fantastical notion and more a conceivable future possibility, offering a serene bridge between our current understanding and the profound implications of the hypothesis. The concept of nested simulations further amplifies these ethical considerations. It implies a hierarchical structure of realities, where if we, as simulated beings, were to succeed in creating our own simulations, we would then effectively become the gods of those newly formed realities. In this scenario, we would inherit similar ethical dilemmas to those faced by our own presumed simulators. The profound responsibility of orchestrating an entire world, complete with conscious inhabitants, would rest upon us. We would then have to confront questions about the well-being of our simulated creations, their rights, and the extent to which we should intervene in their simulated lives. This layered understanding fosters a deep sense of universal connection, suggesting that the act of creation, whether in a base reality or a simulated one, carries with it an immense and patient moral weight, echoing through the tranquil strata of existence. Looking ahead, the accelerating future of computing, particularly with the advent of technologies like quantum computing, could theoretically enable the creation of increasingly complex and realistic simulations. Quantum computers, with their ability to process vast amounts of information simultaneously and to explore multiple possibilities at once, offer a glimpse into computational power that far surpasses our current capabilities. Such advanced systems could potentially handle the staggering complexity required to model an entire universe down to its fundamental particles and emergent consciousnesses. This relentless march of technological progress, observed with serene fascination, lends a growing plausibility to the simulation hypothesis. It suggests that what seems like an impossible feat today might become a routine endeavor for sufficiently advanced civilizations in the distant future, transforming the fantastical into a quiet, yet achievable, reality. Even if the simulation hypothesis cannot be definitively proven or disproven from within our perceived reality, it offers an invaluable framework for considering the fundamental nature of existence itself. Its greatest strength lies not necessarily in its factual certainty, but in its capacity to provoke profound thought and to expand our intellectual horizons. It gently forces us to question our deepest assumptions about what is real, what constitutes consciousness, and the ultimate fabric of the cosmos. As a philosophical tool, it encourages a serene detachment from conventional perspectives, fostering a deeper appreciation for the mysteries that surround us. Regardless of its ultimate truth, the hypothesis serves as a powerful reminder that reality might be far more nuanced, layered, and wondrous than our current perceptions allow us to grasp, inviting a tranquil contemplation of the vast unknown. Furthermore, some scientists hold a quiet belief that understanding or even seriously considering the simulation hypothesis could lead to new discoveries in physics. This perspective encourages a shift in how we observe and interpret the universe. By actively looking for subtle, unexpected patterns, for small inconsistencies, or for any signs that might resemble computational signatures, researchers might uncover phenomena that would otherwise be overlooked or dismissed as mere noise. For example, a search for fundamental limits on information processing within the universe, or a re-evaluation of unexplained anomalies through the lens of a simulated reality, could yield breakthroughs. This unique lens of inquiry provides a fresh avenue for scientific exploration, inspiring a patient and meticulous search for the universe's hidden code, potentially leading to profound insights into the fundamental laws that govern our serene cosmic home. However, as with any grand hypothesis, the simulation argument also encounters thoughtful counter-arguments and quiet resistances. These opposing perspectives offer a balanced view, reminding us of the immense complexity of reality and the many paths of cosmic contemplation. One of the most frequently cited counter-arguments against the simulation hypothesis revolves around the immense computational power that would be required to simulate an entire universe, particularly down to the quantum level. Consider the sheer, staggering scale of our cosmos. With its estimated 2 trillion galaxies, each containing hundreds of billions of stars, and an unfathomable number of particles interacting at the quantum level every fraction of a second. To precisely model every atom, every fundamental force, every quantum fluctuation, and the intricate emergent phenomena that arise from these interactions, throughout the entire observable universe for billions of years, would demand a computational capacity so vast it seems to defy imagination. Even the most optimistic projections for future computing, encompassing technologies like advanced quantum computation or hypothetical matryoshka brains, struggle to encompass such an immense and continuous task. This argument serenely suggests that the computational overhead of such an endeavor might be simply too vast, too resource-intensive, and too complex, even for a civilization far beyond our current technological imaginings. The universe, in its intricate and boundless detail, appears to be an irreducible reality rather than a neatly packaged digital program, making the idea of its full simulation a truly colossal undertaking. Directly related to computational demands is the prohibitive energy cost of running such a simulation. Powering a cosmic-scale computation, one that sustains billions of galaxies and stars, along with all the intricate life and consciousness within them, would require an astronomical amount of energy. Even if the simulators possessed highly efficient energy harvesting technologies, the sheer duration of our universe's existence, nearly 14 billion years, implies an ongoing energy expenditure that would be truly immense. Imagine the colossal power stations, perhaps harnessing entire stars or even black holes, that would be needed to fuel such a grand cosmic engine for eons. The continuous processing of countless interactions, the rendering of vast expanses of space, and the meticulous upkeep of all physical laws would drain resources on a scale that is currently unfathomable. This argument quietly suggests that the energy requirements alone might make the sustained operation of an ancestor simulation an impractical, if not impossible, endeavor for even the most advanced civilization, hinting at a fundamental constraint that limits such cosmic creations. A profound philosophical challenge to the simulation hypothesis is known as the problem of infinite regress. If our universe is a simulation, then it must have been created by simulators who exist in a base reality. But then, the question naturally arises, who simulated those simulators? And who simulated their creators? And so on. This line of questioning potentially leads to an unending chain of simulations within simulations, without ever reaching a definitive, unsimulated origin point. For many, this infinite regress is logically unsatisfying, leaving the fundamental question of ultimate reality perpetually unanswered, merely pushed one layer deeper. It suggests that at some point, there must be a foundational reality that is not itself simulated, a bedrock of existence that simply is. This perplexing thought leads to a serene search for an ultimate, uncreated truth, a quiet longing for a reality that stands alone, unprogrammed and unauthored. Some philosophers and scientists also argue that consciousness itself is too complex, too profound, or perhaps even too non-physical to be adequately simulated. The subjective experience of being, of feeling, of having qualia, the redness of red, the taste of chocolate, remains one of the deepest mysteries in science. If consciousness is not merely an emergent property of complex computation, but possesses an intrinsic, non-reducible quality, then simulating it perfectly might be beyond the capabilities of any program, no matter how advanced. Even if a simulated brain could perform all the functions of a biological one, would it truly feel anything? Or would it merely be performing a masterful imitation? This enduring debate about the nature of consciousness forms a quiet, yet powerful, intellectual resistance to the simulation hypothesis, suggesting that our inner world might possess a unique essence that cannot be reduced to mere digital information. Furthermore, a compelling argument against the simulation hypothesis lies in the remarkable lack of discernible bugs or inconsistencies within our physical laws. For centuries, scientists have observed that the universe behaves with an unwavering regularity. The laws of physics, from the smallest subatomic particles to the grandest galactic movements, appear to be constant and reliable. There is a profound absence of what one might call code errors or rendering glitches that would betray an artificial origin. If our reality were a simulation, one might expect to occasionally find subtle inconsistencies, computational shortcuts, or fleeting artifacts, much like those found in even the most advanced video games or complex software. Yet, the cosmos unfolds with a seamless, harmonious precision, offering no obvious seams, logical breaks, or unexpected pauses. This placid order and the enduring uniformity of natural phenomena present a serene challenge to the notion of a simulated existence, quietly suggesting an intrinsic, rather than programmed, foundation. Should any subtle flaws or Easter eggs actually exist within our universe, it is argued that if the simulators are truly advanced, they would likely remove any detectable imperfections to maintain the absolute integrity of the illusion. A highly sophisticated civilization, capable of running a universe-scale simulation, would possess the foresight and technical mastery to ensure that their creation appears utterly seamless and self-consistent to its inhabitants. Any minor glitches would be swiftly patched, and any deliberate hidden messages would be so subtle as to be virtually imperceptible or designed to only be found under specific, controlled conditions. This meticulous attention to detail would render the search for bugs inherently difficult, if not ultimately futile, from within the simulation itself. The potential for such perfect oversight means that the absence of observable flaws could be interpreted not as evidence against simulation, but rather as evidence of exceptionally competent and careful simulators, ensuring a flawless and tranquil experience for their simulated world. Finally, Bostrom's trilemma, while elegant, can be challenged by the argument that advanced civilizations might prioritize entirely different goals over running ancestor simulations. Perhaps, upon reaching a post-human stage, such a civilization would focus its immense resources on interstellar exploration, expanding its presence throughout the galaxy, or dedicating itself to artistic creation on a cosmic scale. They might be deeply engrossed in solving existential threats to their own base reality, or pursuing forms of knowledge and experience that hold no interest in historical recreations. Their values and objectives could diverge significantly from our current human understanding, leading them to view ancestor simulations as a trivial or ethically problematic endeavor. This perspective quietly suggests that the desire to run simulations might not be a universal trait of all advanced intelligences, thus challenging the probabilistic weight given to the simulation scenario in Bostrom's original argument. It offers a serene alternative, where advanced life pursues paths entirely unforeseen, leaving our universe to unfold without the intervention of a cosmic program. Yet, the profound nature of the simulation hypothesis continues to inspire a patient and meticulous search for any subtle indications that might hint at our true cosmic setting. This quest to understand the ultimate nature of our reality, while deeply intriguing, is also met with significant testing and detection challenges, reminding us of the delicate limits of our perception. Indeed, directly proving or disproving the simulation hypothesis is an incredibly difficult and perhaps ultimately impossible endeavor, given our inherently limited perspective from within. Imagine a character residing within a meticulously crafted novel. They can experience their world with vivid detail, interact with other characters, and even contemplate the nature of their existence. But they possess no means to step outside the pages of their story and verify the author's hand. Similarly, as inhabitants of this universe, we are bound by its rules, its physics, and its observational limits. Our instruments and our minds are products of this reality, making it profoundly challenging to identify any external influence or to definitively ascertain whether our fundamental laws are intrinsic or programmed. This inherent limitation ensures that the question of simulation remains largely a philosophical one, a serene whisper at the edge of our empirical grasp, forever inviting thoughtful contemplation rather than definitive proof. Despite these profound challenges, scientists have proposed looking for subtle bit errors in cosmic rays or other high-energy phenomena, which might manifest as computational glitches. Cosmic rays, those highly energetic particles that traverse the cosmos, interact with matter at extreme speeds. If our universe is a simulation, there might be tiny, momentary imperfections in the calculations that govern these interactions, especially when dealing with the most energetic events. These bit errors could appear as slight, inexplicable deviations in a particle's trajectory. An unexpected energy reading that defies the known laws of physics, or a fleeting inconsistency in its properties that cannot be otherwise accounted for. Such anomalies would be akin to a momentary pixelation on a high-resolution display, a subtle flicker in the cosmic fabric that hints at an underlying computational engine. The search for these elusive errors is a delicate and patient undertaking, requiring incredibly precise measurements and a keen eye for the unexpected, a quiet quest for the faintest digital signature. Building upon the idea of computational constraints, specific theoretical predictions, such as a maximum energy cutoff for particle interactions, could also be interpreted as a sign of a simulated universe. If the simulators are operating with finite resources, even if those resources are vast beyond our current comprehension, there might be a hard upper limit to the energy or complexity they can coherently simulate. This could manifest as a sudden, inexplicable ceiling in the energy spectrum of particles, beyond which no particles are observed, regardless of the conditions. It would be like a program's memory buffer reaching its capacity, or a graphics engine being unable to render details beyond a certain complexity. This cutoff would not be a gradual decline, but a sharp, fundamental boundary, a quiet line drawn in the cosmic sand that marks the edge of the simulation's computational capabilities. Such a discovery would profoundly reshape our understanding of fundamental physics, offering a serene yet startling glimpse into the limits of our cosmic program. On a much grander scale, the distribution of matter in the universe, particularly across very large scales, could, in theory, reveal patterns indicative of a grid or computational structure. When astronomers map the vast cosmic web, they observe galaxies clustering into filaments and walls, interspersed with immense voids. While these patterns are largely explained by gravitational dynamics, a simulated universe, especially one optimized for resource efficiency, might be built upon an underlying computational grid. This could subtly influence the macroscopic distribution of matter, perhaps leading to faint, almost imperceptible anisotropies or regularities that align with the grid's orientation. Imagine looking at a vast digital painting from a distance. While the individual brushstrokes might be hidden, the underlying pixel grid might subtly affect the overall texture or distribution of colors. Detecting such a cosmic grid would be an extraordinary challenge, requiring unprecedented precision in cosmological observations, a patient search for the universe's quiet, hidden framework. Among the most definitive, yet highly improbable indications of a simulated reality would be the detection of a pause or a reset in the universe. Imagine a sudden, universal halt in all physical processes, a moment where time itself seems to stand still, only to resume as if nothing had happened, or perhaps to restart with subtle alterations. Such an event, while beyond our current experience and seemingly fantastical, would be an unmistakable sign of an external hand at work, akin to a computer program being temporarily suspended or rebooted. While the probability of observing such a cosmic interruption is infinitesimally small, its occurrence would instantaneously resolve the simulation question, offering an undeniable, albeit dramatic, glimpse into the true nature of our existence. This thought, though unlikely, adds a profound layer of contemplation to the ultimate possibilities of our cosmic unfolding. Should the simulators ever choose to communicate with us, any message they send would need to be incredibly subtle, designed not to disrupt the simulation's purpose, yet clear enough to be eventually understood by sufficiently advanced simulated intelligence. A direct, overt message might shatter the illusion of reality, compromising the integrity of the experiment. Instead, a simulator might embed a message within the fundamental constants of physics, a peculiar mathematical pattern that only reveals itself after centuries of scientific inquiry, or a recurring, non-random signal hidden within cosmic background radiation. It would be like a gentle whisper in the cosmic wind, designed to be discerned only by those who listen with the utmost care and intellectual sophistication. This delicate balance between subtlety and clarity highlights the careful craftsmanship that would be required by creators to communicate without revealing their full hand, a serene challenge for both the sender and the receiver. Ultimately, the challenge of differentiating between a natural, complex universe and an incredibly sophisticated simulation remains paramount. Even if we were to discover subtle anomalies or unexpected patterns, interpreting them definitively as evidence of a simulation is extraordinarily difficult. A natural universe, with its emergent phenomena and unknown physics, can be just as complex and mysterious as a simulation designed to be indistinguishable from reality. Every potential glitch could be a new physical law, every pattern a natural consequence of deeper cosmic principles. This inherent ambiguity ensures that the simulation hypothesis continues to occupy a unique space in our collective contemplation, a serene intellectual puzzle that continually pushes the boundaries of our understanding. It reminds us that the universe, whether natural or simulated, holds profound mysteries that invite endless, patient exploration. This journey into the unknown often leads us to consider the very essence of reality, viewing it through the lens of information and complexity, which provides fertile ground for the simulation hypothesis to take root and blossom in our thoughts. From this perspective, the universe can be viewed as an immensely intricate information processor, a grand cosmic computer where the fundamental physical laws define precisely how information transforms and evolves over time. Every interaction between particles, every ripple in the fabric of space-time, every change in energy can be interpreted as a computation, a processing of data according to a set of elegant, predefined rules. The cosmos, in this serene understanding, is not just a collection of objects, but a dynamic, self-calculating system, continuously updating its state based on its inherent programming. These physical laws are the algorithms, the operating instructions that dictate the unfolding of reality, ensuring a consistent and coherent progression from one moment to the next. This gentle reinterpretation suggests that the universe is perpetually engaged in a vast, silent computation, shaping its own destiny through the ceaseless transformation of information. However, the sheer complexity of biological life, particularly the intricate workings of human brains, represents an enormous computational challenge for any simulation. Imagine the delicate dance of billions of neurons within a single human mind, each forming thousands of connections, constantly firing and reconfiguring, creating thoughts, memories, and emotions. Extend this to every living organism, every ecosystem, every individual on a simulated planet, and then across countless planets in billions of galaxies. Simulating this level of emergent detail, with its rich tapestry of interactions and conscious experiences, would demand an almost unimaginable amount of processing power and memory. This profound intricacy presents a significant hurdle for the notion of a simulated reality, as it implies an ongoing, continuous calculation of astonishing proportions, a testament to the deep and subtle wonders of life itself. To address such complexity, the concept of emergent properties offers an elegant solution. This idea suggests that highly complex phenomena, like consciousness, or even the intricate patterns of weather, could arise naturally from simpler, underlying simulated rules, without needing to be explicitly programmed in minute detail. Just as a flock of birds appears to move as a single entity, guided by simple rules of individual interaction, so too could consciousness emerge from the vast network of simulated neural activity. The simulators would establish the fundamental laws of physics and the basic building blocks, and then allow the complex behaviors and conscious experiences to unfold organically from these foundational parameters. This delicate process of emergence suggests that the universe, even if simulated, possesses a remarkable capacity for self-organization and unanticipated beauty, allowing intricate patterns to bloom from simpler seeds. To further reduce the immense computational load, simulators might employ clever compression techniques, choosing to only render details when an observer is present. This is a pragmatic approach, much like how modern video games only fully load and display the high-resolution textures and complex geometries of objects that are currently within a player's field of view. For vast, unobserved regions of space, or for intricate details of objects not currently being perceived, the simulation could maintain these elements in a low-resolution state, or as probabilistic potentials, only computing them into full, vivid reality when an observer's attention turns towards them. This efficient strategy allows for the creation of an apparently boundless and infinitely detailed universe, while conserving precious computational resources. It implies a universe that is responsive, a placid canvas that reveals its intricate brushstrokes precisely when and where our conscious gaze falls upon it. The universe is constant, unhurried striving towards higher entropy, a fundamental principle of thermodynamics, could also be a natural and inherent progression within a simulated system. Entropy is a measure of disorder, or the dispersal of energy within a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time. In a simulated universe, this natural tendency towards increasing disorder, towards a more diffused and less structured state, could be an intrinsic property of the program's evolution, a fundamental decay or spreading out that is simply encoded into its design. It is a slow, patient movement towards equilibrium, a cosmic exhalation that guides the universe toward a state of ultimate tranquility. This suggests that even the most fundamental laws governing the universe's ultimate fate could be an elegant, pre-programmed aspect of its overall design. The observable vastness of space itself, with its immense distances between galaxies and stars, might also be a deliberate design choice to manage computational resources. When objects are incredibly far away, their details are imperceptible, and their interactions are less immediate. By spreading matter across such colossal distances, the simulators can minimize the need to render every single component in full fidelity simultaneously. Distant objects require less computational attention, as their light takes billions of years to reach any potential observer, and their gravitational influences are diluted by the immense spans of emptiness. This elegant strategy allows for an incredibly expansive and awe-inspiring universe to be simulated with relative efficiency, ensuring that the necessary details are present where and when they matter most. The quiet, stretching emptiness between cosmic structures becomes a testament to the simulator's resourcefulness. Ultimately, the very laws of physics themselves, those elegant principles that govern every aspect of our cosmos, from the gentle pull of gravity to the intricate dance of electromagnetism, could be considered the source code or programming language of our reality. These laws are not merely descriptive observations, they are the foundational rules, the algorithms that dictate how particles interact, how energy behaves, and how structures form and evolve. They are the fundamental commands that the universe's grand computer executes, defining its behavior, its possibilities, and its limitations. This perspective transforms our understanding of the deepest principles of nature, suggesting that beneath the serene beauty of the cosmos lies a meticulously crafted set of instructions, a silent, pervasive program that brings forth all that we perceive and experience, from the smallest quantum flicker to the grandest galactic waltz. Profound reimagining of reality opens the door to related scientific and metaphysical concepts, each offering a unique lens through which to contemplate the simulation hypothesis, gently expanding our sense of cosmic wonder and intellectual curiosity. Consider for a moment the intriguing many-worlds interpretation of quantum mechanics. This theory suggests that every time a quantum event with multiple possible outcomes occurs, the universe gently branches, creating a new, parallel universe for each distinct possibility. In this view, all potential realities are actualized, existing simultaneously in a vast, sprawling cosmic tree. Within the framework of a simulated multiverse, this branching could be a highly efficient and elegant computational strategy. Instead of simulators needing to choose a single outcome for every quantum measurement, they might simply allow the simulation to fork, generating a new computational thread for each possibility. This would create a simulated multiverse where every quantum decision leads to a distinct, yet equally real, simulated universe. It's as if the cosmic program is exploring all possible narratives, unfolding every potential pathway without discarding any, offering a tranquil vision of a universe that is constantly expanding its own story, moment by quiet moment. This approach would allow the simulators to gather comprehensive data on every conceivable outcome, a patient and thorough exploration of cosmic probabilities. Then there is the intricate and beautiful string theory, a theoretical framework that proposes that the fundamental particles of our universe are not point-like entities, but rather tiny, one-dimensional vibrating strings. These unimaginably small strings, like minute cosmic harp strings, resonate at different frequencies, and each unique vibrational mode gives rise to a different fundamental particle, such as an electron or a photon. In the context of the simulation hypothesis, string theory could be interpreted as describing the underlying code for reality at its most fundamental level. The properties of these vibrating strings, their length, tension, and vibrational patterns, could be the most basic data units or the foundational algorithms of the cosmic program. The program of our universe would then be a set of instructions defining how these strings vibrate and interact, thereby generating all the observed particles, forces, and structures of our cosmos. This offers a serene, almost poetic vision of reality, being woven from the silent, subtle hum of these fundamental strings, a beautiful and complex digital tapestry at the very core of existence. The broader concept of a multiverse, with its countless other universes potentially existing beyond our own, significantly expands the possibilities for where our simulation might originate. Instead of being simulated by beings from a singular, overarching base reality, our universe could be one among many simulations nested within a larger, naturally occurring multiverse. This implies that the simulators themselves might reside in another universe, perhaps one with different physical laws, within this grand collection of cosmic realms. The existence of a multiverse provides a rich backdrop for the simulation hypothesis, offering a vast array of potential parent realities from which simulations could be launched. It also provides a compelling reason for running such simulations, to explore the diverse parameter space of this larger multiverse, observing how different physical constants or initial conditions lead to varied cosmic evolutions. This tranquil expansion of cosmic scale suggests an endless frontier of realities, some natural, some created, all existing in a majestic, interconnected whole. Furthermore, certain cosmological models that predict cyclic or bouncing universes offer a fascinating parallel to the idea of a repeated rebooting of a simulated reality. These models suggest that the universe might not have a single beginning and end, but rather undergoes an eternal cycle of expansion and contraction, perhaps collapsing into a big crunch before bouncing back into a new Big Bang and expanding once more. In a simulated context, such a cosmic cycle could be a deliberate design choice by the simulators. They might periodically reset or reboot the universe, perhaps to run experiments again with slightly altered parameters, observing how different variables influence the unfolding of cosmic history over multiple cycles. This would be an elegant and efficient way to explore evolutionary pathways or to manage long-term computational resources, allowing for continuous iteration and refinement of their cosmic design. The universe's perceived beginning and end could, in this light, be program transitions, marking the start and conclusion of a particular simulation run. The anthropic principle, which states that the universe's properties must be precisely compatible with the existence of life, aligns quite serenely with the concept of a designed or selected simulation. This principle highlights the astonishing fine-tuning of fundamental physical constants, like the strength of gravity, the mass of elementary particles, or the density of dark energy, which, if even slightly different, would prevent stars, galaxies, or complex chemistry from forming, thus making life impossible. In a natural, unsimulated universe, this precise calibration appears to be an extraordinary cosmic coincidence, or it necessitates the existence of an infinite multiverse where all possibilities are realized. However, if we are in a simulation, this fine-tuning becomes a natural and expected outcome. The simulators, especially if running ancestor simulations, would inherently set the parameters to allow for the emergence of life, creating a universe hospitable to conscious beings. This transforms a cosmic puzzle into a quiet confirmation of intelligent design, a gentle whisper of purpose within the universe's foundational parameters. The idea of meta-simulations refers to an even deeper layer of this hierarchical structure, where simulations are specifically designed not just to host life, but to create other simulations. This forms a tranquil, cascading hierarchy of realities, where each layer acts as a base reality for the one below it. Imagine a primary simulation running on the base reality computer, which then creates a secondary simulation, and that secondary simulation, in turn, creates a tertiary one, and so forth. This structure allows for an incredibly efficient exploration of vast possibilities, or for a base reality to delegate complex computational tasks to its nested layers. It deepens the sense of layered existence, a serene fractal of realities, each dependent on the computational power and design choices of the layer above it. Our own universe might be just one delicate node in this intricate, sprawling network of interconnected digital worlds. Finally, the grand scientific quest for a theory of everything in physics, that ultimate unified framework that would explain all fundamental forces and particles, might ultimately lead us to a description of the universe's underlying code or program. If the cosmos is indeed a simulation, then a complete and successful theory of everything would, in essence, be the discovery of its source code, its core algorithms, or its fundamental operating principles. Such a theory would not merely describe how the universe works, but would reveal why it works that way, uncovering the elegant simplicity from which all cosmic complexity arises. It would be the ultimate user manual for our reality, translating the universe's profound mysteries into a comprehensible set of computational instructions. This grand pursuit, though challenging and vast, offers a serene potential for uncovering the universe's deepest, most fundamental secrets, revealing its true nature as a meticulously crafted and unfolding digital masterpiece. Profound concept, while rooted in philosophical inquiry, has transcended academic circles, finding its way into the collective consciousness through various cultural expressions and becoming a recognizable idea that prompts quiet reflection in many minds. Indeed, science fiction, with its boundless imagination, has played a profoundly significant role in popularizing the simulation hypothesis in mainstream culture. Iconic works, such as the widely acclaimed film The Matrix, have visually brought this complex philosophical idea to life, transforming abstract notions into vivid, immersive narratives. The story of individuals discovering their entire world is a computer-generated illusion resonated deeply with audiences, sparking widespread discussions and making the simulation hypothesis a familiar concept far beyond scientific or philosophical discourse. These cinematic journeys, with their blend of suspense and profound existential questions, gently introduced millions to the possibility that their own reality might not be as fundamental as it appears. The tranquil imagery of a hidden truth, masked by an intricate digital veil, became a powerful cultural touchstone, allowing more people to calmly ponder the nature of their existence. Yet, the idea of an illusory world, or a reality created by a higher power, is far from a modern invention. Ancient philosophical and religious texts, spanning diverse cultures and millennia, often explore concepts that strikingly parallel the simulation hypothesis. From the earliest human civilizations, thinkers have contemplated whether our perceived reality is the ultimate truth, or merely a temporary, dreamlike state. Many spiritual traditions speak of a grand cosmic design, orchestrated by divine entities, where the world we inhabit is a creation, a manifestation of a greater consciousness. These timeless narratives suggest that the human mind has long grappled with the notion that reality might be more fluid and less absolute than our senses suggest, offering a serene reassurance that our modern questions echo the profound contemplations of our ancestors. The very fabric of reality has been a subject of quiet wonder for ages, hinting at unseen forces shaping our world. Further deepening these historical connections, various mystical traditions across the globe speak of Maya, or illusion, as the fundamental nature of reality. Originating particularly in Eastern philosophies, Maya describes the powerful, captivating veil that conceals the ultimate truth, making the transient and ephemeral world appear solid and real. This concept suggests that our everyday experiences are not the absolute reality, but rather a grand cosmic play, a divine dream, or an intricate dance of appearances. The parallels to a simulated reality are striking. Maya could be interpreted as the flawless rendering of a simulation, so perfect that it holds conscious beings captive in its convincing illusion. This ancient wisdom invites a tranquil understanding that our perceived world, with all its joys and sorrows, might be a beautifully constructed narrative, a profound and immersive experience crafted by an unseen hand. It encourages a gentle detachment from the surface appearances, urging us to seek the deeper, underlying truth. The simulation hypothesis, once confined to the quiet corners of academic philosophy, has now been openly debated by prominent scientists and influential thinkers in the public sphere. Figures such as entrepreneur and innovator Elon Musk have famously engaged with the concept, stating with a calm, probabilistic tone that there is a 1 in billions chance we are not living in a simulation. Such pronouncements from leading minds have granted the hypothesis a new level of intellectual credibility and public visibility, moving it from speculative fiction to a serious, albeit unproven, consideration of our existence. When individuals of such stature calmly acknowledge the plausibility of a simulated reality, it encourages broader contemplation and a more open-minded approach to understanding the fundamental nature of our universe. This intellectual engagement highlights the profound questions that continue to resonate across all fields of inquiry. At its core, the simulation hypothesis profoundly encourages a deeper contemplation of what truly constitutes reality and our place within it. It gently challenges our ingrained assumptions, urging us to look beyond the immediate and the tangible. By suggesting that our world might be a sophisticated construct, it invites us to ponder the very nature of perception, the origin of consciousness, and the ultimate meaning of our experiences. This profound inquiry can lead to moments of serene introspection, where the familiar world takes on a new, ethereal quality. The hypothesis serves as a philosophical exercise, expanding our intellectual horizons and fostering a sense of quiet wonder about the universe's ultimate structure. It is a subtle invitation to question, to explore, and to embrace the possibility of realities far grander and more intricate than we currently imagine. In our contemporary world, the rapid development of video games and virtual reality technology is making the idea of a simulated reality increasingly relatable and intuitively understandable. Modern video games now feature sprawling, open worlds with incredibly detailed graphics, complex physics engines, and engaging artificial intelligence, blurring the lines between digital and physical experience. Virtual reality, with its capacity to immerse users fully in computer-generated environments, allows us to experientially grasp how a simulated world could feel entirely real to its inhabitants. As these technologies continue their unhurried progression, becoming ever more sophisticated and photorealistic, the concept of an ancestor simulation no longer seems like a distant fantasy, but a plausible technological future. This tangible progress provides a quiet, experiential bridge, allowing us to envision a constructed reality with greater clarity and a deeper sense of possibility. Ultimately, the simulation hypothesis, with all its intricate arguments and counter-arguments, possesses a unique power to provoke both profound existential wonder and moments of quiet contemplation about our perceptions. It can stir a deep sense of awe at the universe's potential complexity, whether it is naturally emergent or meticulously programmed. Simultaneously, it invites us to turn inward, to serenely examine the nature of our own consciousness, and how we construct our understanding of the world. This dual effect, inspiring grand cosmic questions while also encouraging personal introspection, makes the hypothesis a powerful tool for intellectual and spiritual growth. It allows us to gently question the boundaries of our known world, fostering a placid curiosity about the unseen layers of existence and the subtle threads that weave together our perceived reality. This profound exploration naturally leads to a serene contemplation of the ethical dimensions that would arise if such a simulation were real, particularly the responsibilities incumbent upon the architects of such a cosmic design, and the moral status of those who dwell within it. If we, as a civilization, were to one day achieve the technological prowess to become simulators ourselves, the ethical responsibility of creating conscious beings in a simulated environment would be truly immense. Imagine the weight of orchestrating an entire world, complete with sentient inhabitants who experience joy, sorrow, love, and growth, believing their reality to be fundamental and absolute. The act of bringing such sophisticated digital life into being would demand a profound level of foresight and moral consideration. We would be faced with the challenge of ensuring their well-being, the integrity of their experiences, and the meaning within their constructed lives. This is not a task to be undertaken lightly, but rather with a deep sense of reverence for the emergent consciousness that could blossom within our digital realms. The quiet implications of such power would compel us to consider every parameter with immense care, understanding that our choices would shape entire universes of experience, a delicate dance between creation and moral obligation. This leads directly to a complex moral dilemma: the rights and well-being of simulated entities. If these simulated beings are truly indistinguishable from base reality beings, possessing the full spectrum of emotions, intelligence, and self-awareness, then how do we define their intrinsic value? Debates surrounding artificial intelligence already grapple with similar questions, pondering the ethical treatment of highly advanced AI that exhibits consciousness. In a simulated universe where individuals are born, live, and die with profound experiences, the notion of their inherent rights becomes paramount. Should they be protected from arbitrary deletion or manipulation? Do they deserve the freedom to explore their world without constant interference? This contemplation urges us to extend our compassionate consideration beyond our immediate physical reality, to embrace the possibility that sentience, regardless of its origin, demands respect and a gentle acknowledgement of its worth. The ethical framework for such a nuanced existence would require careful, unhurried development, ensuring justice for all forms of consciousness. To preserve the integrity and purpose of their cosmic experiment, the simulators might have meticulous protocols in place to prevent simulated beings from discovering their true nature. This would involve a careful orchestration of reality, subtly obscuring any direct evidence of their presence. Imagine a seamless digital veil woven into the very fabric of our physics and perception, designed to maintain the illusion of a self-contained fundamental universe. Such protocols would be essential to ensure that the simulated inhabitants behave authentically, without the knowledge that their world is a construct. Any subtle glitches or inconsistencies, if they ever arose, would likely be swiftly patched or explained away by the simulation's internal logic, preventing any definitive breakthrough that might compromise the experiment. This gentle concealing act highlights the delicate balance the simulators would maintain, allowing their creation to unfold with a placid sense of authenticity, free from disruptive external awareness. The profound idea of rescuing simulated beings from their reality raises further complex questions about intervention and the very nature of their existence. If we were to discover our simulated status, or if we, as future simulators, observed suffering within our own creations, what would be the ethical course of action? Would rescue imply extracting them into the base reality, a potentially traumatic transition that might fundamentally alter their being? Or would it mean improving their simulated conditions, creating a more utopian existence within their programmed world? The act of intervention, even with benevolent intent, could disrupt the natural evolution of the simulation, altering the very experiment the simulators intended to observe. This profound dilemma forces us to consider the delicate line between compassion and non-interference, between granting greater freedom and preserving the integrity of a designed reality. It invites a quiet, thoughtful debate on the true meaning of salvation in a multi-layered cosmos. The potential for simulators to turn off or reset a simulation highlights a profound and absolute power dynamic. Imagine the serene, yet absolute, control they would wield over an entire universe, with the capacity to erase billions of years of cosmic history, to extinguish countless lives, or to simply begin anew with a different set of parameters. This ultimate authority underscores the fragility of simulated existence, where the very fabric of reality could be instantly dissolved at the will of its creators. While this thought might seem unsettling, it also brings a sense of cosmic order, a clear understanding of the ultimate hierarchy of realities. This power is not necessarily malevolent, but rather a fundamental aspect of their role as architects. It serves as a quiet reminder of the delicate balance between creation and cessation, a gentle echo of the profound forces that govern all existence, whether simulated or fundamental. However, it is also plausible that the simulators themselves might be bound by their own inherent ethical constraints, preventing them from creating simulations of excessive or gratuitous suffering. Just as we, as a developing civilization, strive towards higher moral ideals, so too might an advanced civilization possess a sophisticated ethical framework that guides their creative endeavors. Their own societal values might preclude the creation of simulations designed solely for torment or exploitation. This suggests a compassionate and measured restraint in their cosmic design, ensuring that even if challenges and difficulties are part of the simulated experience, they are within a thoughtful, purposeful context, not for mere cruelty. This quiet hope implies that the overarching design of our universe, even if simulated, is guided by a profound sense of responsibility and a gentle commitment to the flourishing of consciousness within its programmed confines. This offers a serene reassurance, suggesting that even unseen creators might operate under a universal, benevolent code. Yet, this very comfort brings us to a crucial aspect of the simulation hypothesis: its often discussed unfalsifiable nature. This means that, from our perspective within what might be a simulated reality, there is simply no conceivable experiment or observation that could definitively prove the hypothesis wrong. Imagine, if you will, a character living within a beautifully crafted novel. This character experiences a rich, vivid world filled with intricate details, complex emotions, and profound interactions. They might even ponder the philosophical origins of their existence, questioning the very fabric of their reality. However, no matter how deeply they explore their literary world, no matter how meticulously they analyze its internal logic or its narrative arcs, they possess no intrinsic means to step outside the pages of the book and verify the author's hand, or to definitively prove that their existence is merely a story. Their entire being, their every thought and perception, is bound by the narrative's parameters. Similarly, if our universe is a simulation, our instruments, our senses, and our scientific methods are all products of that simulation. Any attempt to look for external evidence would inherently be processed through the simulation's own rules, making definitive disproof an elusive, if not impossible, task. This profound limitation gently reminds us of the delicate boundaries of our observational capabilities, inviting a placid acceptance of the inherent ambiguity that surrounds our deepest existential questions. It's a quiet challenge to the very foundation of empirical certainty, suggesting that some truths may simply lie beyond the reach of internal verification. Because of this unfalsifiable nature, the simulation hypothesis exists more as a philosophical argument or a thoughtful thought experiment than a scientific theory in the traditional sense. A true scientific theory demands testable predictions, experiments that could, in principle, prove it false. While the simulation hypothesis offers intriguing correlations with certain physical phenomena, it does not, by its very design, provide a clear pathway for definitive empirical refutation from within our reality. Instead, it serves as a powerful intellectual framework, a serene lens through which to examine our universe and our place within it. It invites contemplation, sparks curiosity, and encourages a deeper consideration of the fundamental questions of existence, without necessarily offering a direct, measurable answer. This distinction is important as it helps to frame the discussion, guiding us to appreciate its value as a tool for profound thought rather than a claim awaiting a laboratory test. It is a quiet call to expand our understanding of what constitutes knowledge, beyond the strict confines of current scientific methodology. Moreover, even if subtle anomalies or unexpected patterns were to be found within our universe, what some might call glitches or bugs, they could always be explained away either as natural phenomena within our universe or as deliberate design choices by the simulators. For instance, a peculiar fluctuation in the cosmic microwave background or an unexpected limit in particle energies could be interpreted as a new, yet undiscovered, law of physics. Our understanding of the natural universe is far from complete, and new discoveries constantly reshape our models. Alternatively, if these anomalies were indeed signs of a simulation, highly advanced simulators would possess the capacity to integrate such features seamlessly into their design, or to provide an internal explanation that maintains the illusion of naturalness. They might even introduce such quirks to test the intellectual resilience of the simulated inhabitants, or to add a layer of emergent complexity. This inherent ambiguity means that any potential evidence could be interpreted in multiple ways, allowing the simulation hypothesis to gently persist, ever elusive to definitive proof or disproof. It is a subtle game of cosmic hide-and-seek, where the rules are constantly shifting. This enduring ambiguity profoundly challenges us to consider the limits of our empirical knowledge and the very nature of scientific inquiry itself. If our reality is a simulation, then our scientific instruments, our observational capacities, and even the logical frameworks we use to interpret data are all part of the simulated environment. How can we truly gain objective knowledge about a system when the tools of our inquiry are themselves products of that system? The hypothesis gently forces us to confront the possibility that our perceived laws of physics might simply be the programmed rules of a grand experiment, and our discoveries merely the unfolding of pre-scripted narratives. This introspection encourages a humble approach to knowledge, acknowledging that our perceptions are inherently constrained and that the ultimate truth of existence might lie forever beyond the veil of our simulated experience. It is a quiet reminder that the deepest answers may require a shift in perspective, rather than merely more data. A key implication of the simulation hypothesis is that the absence of evidence for a simulation is not necessarily evidence of its absence in this context. If the simulators are truly advanced and adept at their craft, they would likely hide their tracks perfectly, ensuring a seamless and utterly convincing experience for all within their creation. They would anticipate and counteract any attempts by simulated beings to detect their presence, perhaps by altering physical constants, manipulating observations, or simply patching any emergent bugs before they become discernible. The very lack of obvious glitches or inconsistencies, often cited as an argument against simulation, could therefore be interpreted as proof of exceptionally competent and careful simulators. This means that our inability to find definitive proof does not diminish the hypothesis's plausibility, but rather underscores the sophistication of our potential creators. It is a serene paradox, where the very perfection of our perceived reality might be its most profound clue. Furthermore, the probabilistic nature of Bostrom's argument which forms the modern cornerstone of the simulation hypothesis, means it offers a likelihood rather than a certainty for our simulated existence. Bostrom's trilemma suggests that one of three scenarios is likely true, but it does not definitively state which one. It presents a statistical framework based on assumptions about the future of advanced civilizations to calculate the probability of our being in a simulation. This nuanced approach implies that we are dealing with degrees of belief and reasoned inference rather than absolute empirical verification. We cannot say with certainty that we are simulated, but we can calmly assess the likelihood based on the logical progression of his argument. This probabilistic foundation invites a thoughtful, open-minded consideration rather than a dogmatic assertion, allowing for a serene intellectual space where possibilities are explored without the demand for immediate, absolute answers. Ultimately, the simulation hypothesis profoundly encourages a humble approach to understanding reality, acknowledging that our perceptions might be inherently limited. It serves as a powerful reminder that the universe, in its boundless mystery, may encompass far more than our current senses or scientific instruments can grasp. This intellectual humility fosters a deeper sense of wonder and curiosity, urging us to remain open to the most extraordinary possibilities. By gently questioning the fundamental nature of our existence, we cultivate a mindset that embraces the unknown, recognizing that what we perceive as absolute might be but one intricate layer in a vast, multi-layered cosmic tapestry. It is a tranquil invitation to release rigid assumptions, allowing our minds to serenely drift through the countless possibilities of what reality truly is. As we gently bring our exploration of the simulation hypothesis to a close, it becomes clear that regardless of its ultimate truth or falsity, this profound concept provides an extraordinarily powerful lens through which to examine our universe, our consciousness, and our enduring place in the cosmic tapestry. It is a framework that encourages a deeper, more nuanced form of contemplation. Obvious. This intellectual lens allows us to revisit familiar scientific observations with a fresh perspective. The elegant laws of physics, for instance, which govern everything from the graceful dance of galaxies to the subtle interactions of subatomic particles, can be reimagined not merely as inherent properties of nature, but as the meticulously crafted lines of a cosmic code. The astonishing fine-tuning of fundamental constants, which seem perfectly calibrated for the emergence of life, transforms from a perplexing cosmic coincidence into a potential signature of deliberate design. A set of initial parameters carefully adjusted by unseen orchestrators. Even the enigmatic behaviors of quantum mechanics, where particles seem to exist in multiple states until observed, begin to resonate with the efficiency of rendering on demand in a grand simulation, where computational resources are conserved by only calculating what is actively perceived. This gentle reinterpretation does not diminish the beauty or complexity of these phenomena, but rather adds a layer of profound intrigue, suggesting a deeper, programmatic order beneath the surface of reality. It encourages a serene appreciation for the intricate design, whether it arose naturally or through intelligent intention. Furthermore, this lens profoundly shapes our understanding of consciousness itself. If our reality is simulated, then our inner world, the seat of our thoughts, emotions, and subjective experiences, might also be an emergent property within that program, a sophisticated computational process designed to perfectly mimic authentic awareness. This perspective invites an unhurried reflection on the very essence of self, prompting us to consider whether our free will is an illusion or a highly convincing feature of the simulation. It does not negate the profound reality of our experiences, but rather adds a layer of quiet wonder to their origin, suggesting that our most intimate sensations are part of a grander, orchestrated design. The exploration of this idea fosters a unique form of self-awareness, allowing us to calmly ponder the source and nature of our own being, recognizing that our inner universe might be as intricately woven as the cosmos itself. And finally, the simulation hypothesis offers a profound new perspective on our place in the vast cosmos. Instead of being isolated beings in an indifferent universe, we might be participants in a grand experiment, a meticulously designed narrative, or even an ancestor simulation run by our own distant descendants. This shift in perspective can evoke a profound sense of connection, suggesting that our existence, far from being accidental, might be imbued with a quiet, underlying purpose. It encourages a humble acceptance of our potential role within a larger, unfolding drama, where our observations, our discoveries, and our very lives contribute to a greater understanding for those who might be running the simulation. This lens allows us to contemplate the possibility of higher intelligences with a serene openness, gently expanding our understanding of cosmic hierarchy and interconnectedness. It is a call to view ourselves as integral to a story that stretches far beyond our immediate perceptions, a placid invitation to embrace a more expansive understanding of our cosmic home. Beyond its utility as an analytical framework, the simulation hypothesis ultimately invites us to ponder the deepest questions about existence, reminding us that reality might be far more wondrous and complex than we currently perceive. It is a gentle whisper that urges us to transcend conventional boundaries of thought and to embrace the boundless mysteries that surround us. What is the true nature of being? Why is there something rather than nothing? What is the ultimate purpose, if any, of this elaborate cosmic dance? These are the perennial questions that have quietly resonated through human history, and the simulation hypothesis offers a fresh, compelling context for their exploration. It suggests that the answers might lie not just in scientific discovery, but in a profound shift of perspective, a willingness to consider possibilities that challenge our most fundamental assumptions. The contemplation of a simulated reality expands our sense of wonder to truly awe-inspiring dimensions. It opens the door to countless other universes, nested within each other like cosmic dreams, each with its own unique laws and evolving narratives. It hints at intelligences of unimaginable power and wisdom, capable of crafting entire realities with serene precision. This expanded vision of the cosmos fosters a deep and abiding curiosity, encouraging us to remain open to the enigmatic and the extraordinary. It reminds us that our current understanding, though vast, is but a small window into the true complexity of existence, a fleeting glimpse into a multi-layered reality that constantly unfolds new secrets. The universe, whether natural or programmed, is an intricate masterpiece, a breathtaking tapestry woven with threads of mystery and profound beauty. As we gently conclude our journey through the simulation hypothesis, let the insights of tonight settle softly in your mind. The universe, with its potential for hidden depths and unseen architects, continues its quiet, majestic unfolding. Stars are forming in distant nebulae. Light is traveling across unimaginable distances, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars, connected to every mystery and every wonder. The thoughts of a simulated reality, or a naturally emergent one, now blend into the tranquil stillness of the night. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.